One major unit in college algebra is exponential equations. I wanted to go over more complex exponential problems that I've encountered. To begin with, I'm going to write down y equals c times b to the x and y equals pe to the rt. So these are the general base equations that are used in the exponential unit, and they can be used to solve almost all of the exponential questions. However, there's one type of question where we can't really outright use these equations on immediately, and those types of questions are half-life questions. So, admittedly, when I saw these for the first time in a long time, I actually wasn't completely sure which equations to use. Well, actually, I started by using these ones, and then I wasn't able to get it. So when I tried Googling just half-life equations, as you can see, it's not so transparent as to which one you're supposed to use, or even I should say which ones you're supposed to use. There's a lot going on here, and when I was working on this in the spring with one of the students, his instructor kind of gave him two equations, and it just wasn't really clicking with him. So what we wanted to try to do was to try to find an alternative strategy towards approaching these half-life problems. And from the combination of looking at the equations like Google, using the instructor's equations, we eventually came up with this. So I'm going to write current amount divided by initial amount equals 2 to the negative t divided by t sub 1/2. And you might be wondering, this doesn't really look that far off from this equation, and you could definitely argue that this is kind of a deviation of p equals p naught 2 to negative t divided by t sub 1/2. And there is a reason why I wanted to write it specifically like this, and we'll see it in just a little bit when we do the half-life problems. But I really like using this equation because we were able to use this to solve all of the half-life questions on the students' written homework, all of the midterm problems, and even some online ones we found. So I just want to, let's actually dive right into it. And actually before that, I am going to rewrite the equation on the top here. So current over initial equals 2 to the negative t divided by t sub 1/2. And again, one of the primary reasons why I think these half-life questions are tough is because you can't use these two base equations immediately. And so let's start with the problem. So suppose 128 ounces decays to 28 ounces in 6 hours. What's the half-life? So if it decays to 28, that means we currently have 28, and that means we start with 128. So we can write 28 divided by 128 equals t, so they tell us 6 hours, so t to the negative 6 divided by t sub 1/2. And now we can proceed to solve for t sub 1/2. And well, actually this will reduce, so this over here will reduce down to 7 over 32 equals t to the negative 6 divided by t sub 1/2. So one of the reasons why I think this another reason why this is kind of tough is because sometimes students aren't familiar with how to clear out this 2, and in that PERT equation, it's more straightforward because you can just use the natural log operator, and oftentimes I've seen with this first equation they might have to do like a radical with some weird, like a third root or a fifth root or something. So anyways, so we're going to clear this 2, of course, by doing the log base of 2 of 7 over 32 equals, so now this will reduce down to -6 divided by t sub 1/2, and so I can write t sub 1/2 will equal -6 all over. So another reason why this is kind of tough too is because sometimes students aren't familiar with how to actually compute this number in their calculators. And if you have an old calculator like mine, you have to use change of base. If they have a newer one, then they usually have the option of being able to change the base. So so by changing a base, this will turn into log 7 over 32 divided by log of 2. And I like the change of base just because it's another option, another tool for the student to solve this in their calculator. If they have an old one like me, they don't have a choice. But it's good to see that they know how to do this, even if they do have the feature where you can change the base. So I'm going to do log of 7 divided by 32 divided by the log of 2, and then -6 divided by my answer, and we get 2.7, around 2.73 hours. So that's pretty neat that we can use, just this one equation to solve this problem. And for the next one, so it has a half-life of this. What's the percent of the original amount of the sample? Now, this is one of the reasons why I like where this will become pretty useful because when we write current over initial, this is the same as representing the original amount as a percentage. And for those who have taken Chem 151 or Chem 152, this is somewhat analogous to doing percent yield, where you have to compare your theoretical against your actual yield. So similar principle for this one. I'm going to write current over initial equals 2 to the negative t divided by t sub 1/2. And if we did try using the p naught and the p, like right here, the student might start kind of getting confused because they actually only give us 2 numbers and we have 4 variables right now. So that's one of the main reasons why we wrote it like this, because this is actually an original amount, the percentage here, which means we can actually just plug the numbers right away, and that will actually just be our answer. So 2 to the negative 1,000 divided by 1620, and I'll plug that into my calculator. 2 raised to the negative 1,000 divided by 1620, and we get 65%. So again, I really like, it's really neat how this equation, it's nice because you don't have to use multiple equations, and you have everything you need within one equation. So this last problem is actually pretty similar to the first one. We're just finding the half-life, so I'm just going to go through on this one a little bit faster, just because now we kind of know the process. So, and this one's actually even nicer because they're actually outright telling us the initial. So, whereas the first one, we kind of had to almost make an assumption, but anyways, so 75 divided by 1,000 equals 2 to the negative 25 2500 over t sub 1/2. So t sub 1/2. I'm kind of skipping some intermediate steps here. So negative 2500 divided by, and I'm going to use the change of base again, log of 75 divided by 1000 over log of 2, and let's plug that in. So negative, actually sorry, I'm going to start with log of 75 by 1000, whoops, divided by the log of 2, and then negative 2500 divided by our answer, and we get something like around 668 years. So just to reiterate, I really like using this half-life equation we came up with. It can solve, it factors in all of these different variables, and you can solve pretty much any application half-life they might throw at you, and you don't have to use multiple equations, and you can do everything just with this alone. So the other rather complex exponential problem that I encountered was this one here. This was also on a midterm review, and what makes this difficult is that so it's actually it's pretty interesting, because they do tell you using a continuous model. So right away you can already assume. So I'm going to rewrite this as pressure as a function of height equals P naught e to the r. Instead of t, I'll use h for height. So most of the time, or most of the exponential problems, they'll usually, like population for example, they might say in 2010 you have a population of 1 million, in 2015 you have a population of 1.5 million, using an exponential model find the population in 2025. And that's usually, so they usually give you like 2 sets of points, and it's pretty nice because usually the first point you can get rid of this e term and then find your initial. But this one's pretty interesting because they don't actually give us any pressure values. They just give us the height values, 18,000. So the key so one of the keys to this problem is recognizing this. So it says the pressure at 18,000 feet is half compared to that of sea level. So in other words, another way of thinking about this is that the pressure at sea level is doubled that of the pressure at 18,000 feet. This is also confusing too, because they don't actually tell us any pressure, and in reality they don't actually need to. It's actually pretty relative, because I mean, I could say the pressure is 25,000 pascals or something, but I like to use simple numbers. So for the sake of simplicity, I'm going to say the pressure at 18,000 is 1. So that would mean the pressure at sea level, this is our 0 reference point, would be 2. Now, if we plug in 0 or 2 equals P naught e to the RH, that term would cancel out to 1, and then our P naught would be 2. And interestingly, so we actually don't have to do that calculation. And the reason why I kind of didn't do that calculation is, again, it doesn't actually matter what pressure values we choose, just as long as we make sure that the pressure at sea level is double that of the height at 18,000 feet. So we still need to, so in order to find the pressure at 1,000 feet though, we still do need to find the R value. So I'm gonna write, so let's write 1 equals 2 e to the 18,000 r, and as you can see, like we're gonna get a 1/2. So I'm gonna kind of skip some steps here. So if you solve for r, you'll end up getting something like the ln of 1/2 divided by 18,000. And if we plug this into the calculator, ln of 1/2 divided by 18,000 we get a very small number. So we know our R though, so this is good. Now that we found the equation, we can find the pressure at 1,000 feet. So what also makes another component which makes this problem difficult is that we're not actually finding the pressure at 1,000 feet. And this kind of goes back to the statement that they kind of can't ask us to, because it's relative, because we designated our own pressure values. So the key is as a percentage of the pressure at sea level. So whatever pressure we find at 1,000 feet, we have to compare it against the pressure at sea level. So I'm going to write this here. Pressure at sea level. So if we plug in 1,000 into our P of H equation, so P of H equals 2E to the, so yeah, this was like 3.85 times like 10 to the negative 5 or something. So if we plug that times 1,000, we'll get, so let's plug that in. So I'm going to write 2 times E raised to our answer times 1,000, and we get 1.92. So this would be, oh, I didn't talk about units, by the way. I chose 1 because I really like atmospheres. So if we compare 1.92 atmospheres against the pressure at sea level, that's just dividing by 2. And then this will eventually equal, so I'm just going to half that, and it's about 96%, which would be our option right here. And interestingly, this is kind of similar to what we were doing in the half-life question. We were doing like the current over the initial, and I think there's a lot of value to doing it like that. But again, this is a tough question because we have to arbitrarily assign our own pressure values, and then we have to compare it against that compared to sea level. So yeah, so I think, and in my opinion, this is honestly, I've tutored a lot of college algebra, and I think this is one of the hardest problems I've encountered in not only in this unit, but even in the entire class. But yeah, so thank you.